First, I'd like to apologize for coming very late to this wonderful atelier. And my plan is to give you a few, let's say, case studies about traveling wave in biological populations that I've been studying with collaborators. And the focus will be, the title of the lectures, in structured population models, where you have a population with some heterogeneity, and you have to take into account this heterogeneity to understand how it propagates. Let me give you one example, which will not be the topic of this today's lecture, but for tomorrow, is when you have a population of bacteria moving in, let's say, in a channel, and when you look into the population with microscope, you will see that they are not going all in the same direction. Okay, and if you look closer, you will see that they are not doing a Brownian motion. They are actually moving with some persistence, and it might be that this persistence is something that you have to care about at the macroscopic scale to understand the speed of the population as a traveling wave. This microscopic heterogeneity in the velocities is something that is important. This is my main goal for this series of lecture, and what I find quite interesting from my point of view is that you have more complex models, but still in many situations, the one I would like to discuss, you can still have, let's say, you can compute the minimal speed in some examples. And you can also unravel some somehow unexpected situations. For example, in some situations, the wave will accelerate, and you can compute rates of acceleration. So this is something I'd like to discuss. And but for today, I wanted as a warm up to present a self-contained case study where there is no structure. So it's a basic, let's say, a parabolic PD, very similar to the KPP one, actually, which occurred a few years ago in a collaboration with biophysicists. And I found it interesting because in one example coming from the biology, from the lab, you find traveling waves with a transition from pulled to pushed, something which is one of the topics of this atelier, and so I found it was interesting. So this let's take it as a warm up, and then tomorrow I will go more into a persistent motion and traveling wave. So my first, and I chose to start because from the mathematical side, it's actually quite, at least what I will present today, I think is very basic. But I thought it was interesting also for the audience to have this example in mind. So it's about aerotactic waves in population of cells which are called dicty. The nickname for them. So it's a joint work with biophysicists, so Cochet-Escartin, Christophe Angard, and Jean-Paul Rieux, who are in Lyon. And they came with some experiment. I will describe the experiment. And at the end of the lecture, I will give you movies of this experiment. And with a PhD student, so those are biophysicists, and a PhD student, Mété Demir-Sigil, who did his PhD on this project. So the idea is that, so as you know, cells, they can move in some preferential direction. So there might be biases due to some signaling. They navigate in some heterogeneous environment with some let's say some signals. You know, it's a very loose description of the environment. And this is named as taxis. Taxis is motion directed by something. So here in my first case study, it's aero taxis, so it's taxis towards oxygen. So you can have, for example, chemotaxis, which is let's say a field in mathematical biology, which is a taxis toward chemicals. Or for today is aerotactics. In this case, the signal, the molecule is oxygen. So common resource in life. And this bias motion is actually at the core of many developmental processes. So it's very well studied in biology, in modeling, in math. And this cell, which true name is dictostellium you might have heard about that. It's very well known for a very salient feature because it's called a social amoeba because it's able to during its life cycle to make a transition from a unicellular to a multicellular, let's say, organism. So it can live as a single cell when usually at least in the lab, the life cycle is initially there is enough resources, and after some time, resource has been consumed, and then the cells are going to gather and to make, let's say, a multicellular organism made of hundreds of thousands of cells. So it's something which has been very well studied for its ability to aggregate in this life cycle. And usually, it's usually studied actually from the mathematical from the point of view of aggregation. And in math, people study usually blow up of solutions. You might have heard about the Keller-Segel equation, which is one equation which has been which was originally proposed by Keller and Segel in the 70s, early 70s. There is and which is very interesting because it's a reasonably simple equation which is able to let's say to capture the basics of cell aggregation. But this is not my focus for today, and today's focus is not on blow-up of solution, which is one particular pattern, very singular, but rather on traveling waves, as I said previously. It's about wave propagation of population under something which is called hypoxia, which is lack of oxygen. So let me describe the experiment, which is a low-tech experiment as far as I could understand from the biophysicist. Yes. So here is a low-tech experiment. You have a plate. You have an initial colony of those deep T cells in the center. And at the initial time, you put a cover glass above your colony. Okay. So it's not permeable to oxygen. So oxygen cannot go through it. So you break the flux of oxygen from above. So oxygen will certainly flow from the lateral. And what will happen after some time, the dicty cell, which are let's say the colony is growing, they will consume all the oxygen around, and because there is no flux from the top, it will soon very soon become limiting. So after some time, you will see you will have what is called a region of hypoxia in the center, and then what you will see a very clear pattern. Let me just not confuse with initial time. So the cover glass is still there, but after some time, you will see your initial colony that will expand with a ring of cells. Few cells are left, let's say, behind, which is now the center of the ring, and the full colony is expanding at some finite speed, and this is over days, which is a very remarkably stable ring, which is expanding at a finite speed with a finite profile. So it's truly a wave for which, of course, you like to understand how it goes and what are the mechanisms of this apparent collective motion, and of course what is the speed depending on the characteristic of your cell population. So again, the cover glass is always there. It's sufficiently large so that after a few days you can even see it by eyes after some time. Okay, so how so this is the experiment. 2 words about the experiment. It was initially, it's a very simple one, but it's a recent one. It was done by some people in Lyon working on cancer cells, and then it was reproduced with those amoeba by this team of biophysicists. And why they are interested in that? They were quite surprised by the ring, and it was not exactly their point. They wanted to understand how cells react at the middle of the colony, the one which are left behind, because those are experiencing very low concentration of oxygen, which is below 1%, which is extremely low, even below. And the idea is to understand how cells are reacting under hypoxia. This might be interesting for the modeling, but let's focus on the ring because it's a nice example of this traveling wave. And let me tell you a little bit of modeling. Very easy. How can you figure out what is going on? As I said, what is important is oxygen. So now I will make, I'm making colors. I will make a section of my experiment. And how I see it, so I will have my X, which is a distance to the center. I will consider it a 1D space, let's say infinitely long. And I imagine that oxygen looks like this. On the lateral side, it's high, around 20%. On the left side is low. It will go to 0 in the mathematical model. In the life, it's below 0.1%. So it's extremely low. So let's consider very low. And if you look with a microscope into the cell population, well, what you will see that if oxygen is high enough, cells will reproduce, and they will move randomly with some, but not that much. Okay, so cell division plus random motion. So very much like in the KPP equation. Okay, but after some time in space, oxygen will drop below some level, and let's call this S0. This has been measured. It's roughly 1% of oxygen. What you will see is that the cells are not going to reproduce anymore. There is not enough energy, but they are going to move actually very clearly, very seriously, very strongly, with a bias in the direction of the gradient of oxygen. Okay, it's a good idea to do so for them, and they are doing that. And this is what biophysicists are very interesting about, how they react to this lack of oxygen. And this, in the model, will happen below some threshold, which will be at some x of t, which I will call interface, which is just a number. Okay, my interface is the point where the oxygen drop below some given threshold, which depends on the cell response to hypoxia. I think I've almost said everything. Now let me take some notations. I will commonly use rho of T of X for the U of Chris' talk, which is a cell density, and S of T of X, the signal, here it's oxygen concentration, which has this profile in my mind. And my model, let's say a minimal, we called it go or grow model, where, of course, you can guess that this is a grow phase, and this is a go. Yes, go or grow. And let me write it. I assume that that oxygen is increasing in space at every time, which corresponds to my picture, which is very a strong, of course, a strong reduction of complexity, but let's take it for granted. And so I will have a random motion without bias, so just a diffusion equation. And then I will have two terms. One is growth. So growth is simply, in our mind, just a linear growth without competition, but limited by oxygen. So this is when S is above some threshold. Okay, as long as oxygen is not limiting, it's fine, and cells will divide. And soon as it's a threshold effect, when it drops below, it's just stop cell division. Okay, and then the counterpart is biased motion, and this one is with a speed chi below some threshold and with constant speed. And here I implicitly assume that because oxygen is increasing, we are going to move to the right. Okay, I should have put here in the original model, I should have a sign of ds over dx, just to say that I'm able to sense the direction of the oxygen and move towards it. But I just simplified that S is increasing in space, so that it's just a +1. Okay, so it's a piecewise, so a few observations maybe. So it's a piecewise linear equation. Either you have S above the threshold, and then you have just, let's say, something which is a linear Fisher-KPP equation. Or you have S below the threshold, and you have just a drift diffusion equation, which is actually conservative. Okay, on the left side, there is no death or no growth of cells. Okay, and the second observation is it's a very weak coupling. With oxygen dynamics. Why? Because it's just true. The position of the interface. If you know the position of the interface, so the interface is when S of x of t is S0. If you know the position of the interface, you can solve this equation directly, okay? So it's a very weak coupling because it's coupling only through a number, position of an interface. And actually, it's so weak that I will not even write the equation for the oxygen dynamics, okay? I will not write it. The result I will present do not depend on the details of the oxygen dynamics. Just let me describe what it goes. It's very easy. Oxygen will diffuse, and it will be consumed by the cells population. Just a diffusion consumption equation, a reaction-diffusion equation with a negative term. But I'm not going to write it because for some reason it does not depend on it. Okay, the only important point is there is a moving interface which is consistent with this profile that will maintain this profile of oxygen, which is an increasing profile at every time. Okay, and just one comment, and it might be the last biological comment of this first lecture. This belongs to the class of what biologists call self-generated gradients, which is very well studied at the moment. It's when cells navigate in some environment by creating their own environment. Okay. Here, what is interesting is the reason why you see the ring sustained for a very long time with a narrow profile with no dispersion in the population is really because the cells are creating their own environment while they are moving. And there are many occurrences in the literature where people are actually arguing that it's a very important process in development because it's much more faithful than having an external gradient if you want to navigate for a very long time. If you want to navigate cross space on a very long distance, if you fix an external gradient initially and just go through it, it must be shallow in some sense because if the distance is very large. On the other hand, if your cell population generates its own gradient while it's moving by consuming something, then the gradient can remain steep all along the journey of the cell population. And then it means that the cell can have a much better response to a local signaling gradient than having an external gradient. So, and they are found in some developing embryo that there is actually this kind of self-sustained wave due to this what they call a self-generated gradient. So this one is a very basic occurrence of it, and I found it quite interesting to show it to you. So, how to construct traveling waves? Now, this is our main. Yes.
Just two questions about how you set up the model. So there's no proliferation when you have movement, right? The chemotaxis in your model.
Yes.
Is that based on measurements or observations, or is that?
No, so it's a very good point. There is actually an overlap.
There's some overlap.
There is some overlap. Okay. This was studied in the biological paper. It does not really change the picture when there is overlap. Except that this model as it is, okay, it does not fit the experiment very well. I will explain at the end of but at least I think for the dynamic of the wave propagation, it captures the key aspects, which is very quickly that depending on the strength of the bias, either the population will be driven by the proliferation at the edge, or will be, let's say, driven more by the bias of cells trying to catch up the oxygen.
Okay, my second question would be also here about why you modeled it this way is about the chemotactic speed.
Yeah.
It's proportional to x, right? Here in this equation.
It's a chi, sorry, it's a number.
Oh, it's a chi.
It's a number. Yeah,
Thank you, that clarifies it.
Yeah, yeah, okay. I want to keep this one because it was related to a Chris notation and in the previous talk. Okay, yeah. But just I was not completely honest in my answer. If you take into account the overlap, then I have no idea how to solve it. All what I will present is really based on the fact that there is this clear dichotomy with a very singular response where you don't see actually the shape of the gradient, just the sign of it. So yeah, it's very for what I'm going to present, it's very important to have this piecewise linear equation with very weak coupling. Okay, but then it's not really sensitive if you look into that. If you do simulations, it's not very sensitive to the shape. So I missed something. Il est là. Ah, thanks. Okay, so I will concentrate on traveling waves. So very basic analysis, and I will postpone the more complicated result to the end. I will just mention that. But let me spend some time to construct the traveling wave, which is something which is, let's say, more construction. It's not because they are completely explicit. So I think it's something which is very common, familiar to most of you. But let's do it for this particular example. And first, I will suppose, which is of course a prerequisite, that the interface is actually moving at some speed c. Okay, of course, if there must be if there is a traveling wave, the environment must move at the same speed. So the oxygen gradient will be shifted at some speed c, and this will be the speed of my interface. And now it's a moving frame. What I have is the usual equation. Let me put d r equals to 1, otherwise I will have too many terms and I will certainly make some mistake. So I will just keep this one. And I put my interface at 0, which is x minus c. Okay, so now I have no coupling anymore. I assume that my interface is moving at some speed c, and that in my moving frame, this is the origin. Okay, by invariance, by transnational invariance, of course, I can choose the interface to be at 0. And as you see, there is no coupling anymore. And this is essentially the reason why I didn't write the equation for the oxygen, because the oxygen will not play any role in the construction of the traveling wave and the determinacy of the speed. Okay, so now it's a piecewise linear equation. I will have to match two exponential solutions because it will be exponential on each side, and I will have to match them. And the matching condition, we have to be a little bit careful because there is some discontinuity, as you noticed. The speed, the advection term is the discontinuous, and we have to ensure that the flux of cells going through the interface will remain continuous. So this is the essential condition we have to make. So we have to care about continuity of the cell flux which means that on the left side, the cell flux, it's a diffusive flux plus advection. So this is the flux on the left side, and this must balance the flux on the right side, which is simply a diffusion because there is no drift on the right side. So it's very classical. What must be continuous is the flux of cells. And actually, this flux of cells is equivalent to the mass balance. At this point, it's interesting first, before computing the density, to make look at the mass balance. So if you integrate this equation across space, and if you look for bounded solution, if you integrate, what does this tell you? So we'll have C minus chi of rho at minus infinity. So you assume it's bounded and that the gradient vanishes at infinity, which means that when you integrate this, there is no boundary at minus infinity, but you get the boundary term coming from the transport. And this must balance the growth. So I said I put it to 1, sorry, which is the integral of rho dz from 0 to plus infinity. So what does this tell you? And this is if, of course, the flux is continuous, because when you make the integration, you have to ensure this condition. This is a net growth of population, which is created on the right-hand side. And this is the flux at minus infinity. So, and there is a flux. It's not like okay, it's a conservative equation, but in some sense, there is a constant creation of cells on one side. And how you can visualize it is that your cell density will look like this. Let me be loose here. And then at minus infinity, you will be essentially flat. What is going on? That you have new cells coming from the division on that side, and those cells are flushed on the left-hand side because the wall density is moving. And this is actually contained in this identity, which comes from the integration of the equation, is that you immediately see here that C is larger than chi by just positivity of that. Yeah. Yeah. The microphone.
Could you explain what is minus infinity in your context, because it's very finite? It's a question of scales between the size of the disk.
So the idea is that I'm looking at the let's say the stationary regime beyond the transient regime. So I assume that the ring is so large that you can forget that and it means that mathematically it would mean that you really ensure that the density profile is flat at the back.
That means that the position of the
ring,
yes, the bound of oxygen is really large.
Yes, yeah. The cover glass is really large, much larger than what the population is going to achieve in a few days. And after a few days, you have a ring which is localized, which has a given width, and which is at very large distance from the center. And I'm looking at this region. Okay, so what means that C is larger than chi? Chi is a speed, transport speed in the original frame, and this tells you that the collective speed is going faster than, let's say, the speed that the cells are able to travel. And so it means that in some sense, it's a very bad news for the cells, because it means that the oxygen, which is actually moving at speed c, is going faster than when the cells are able to move. And it means that the cells are actually flushed behind the front, because if you are looking in the original frame, oxygen is moving faster than the cells. And it explains why, of course, cells are left behind, poor cells, which are left in this area. And if you should now take the point of view of one cell, what will happen? It will grow at some point ahead. It will not move very far because it's only a random unbiased motion. The oxygen concentration is going to pass through. It will try to catch up for a while with this speed chi, but because oxygen is moving even faster, it will be trapped behind, and it will go in this region of hypoxia. Okay, this is what tells you this relationship, which is there. So now let's do it a bit more carefully. And let's take benefit of this piecewise linear structure, because it's a very basic computation. So what happened for z negative? You are looking for exponential solution with some rate lambda. So what you will get the usual thing: c lambda in the first term minus lambda square plus t lambda. So this will be your dispersion relation. Which tells you that either lambda is 0, obviously, or lambda is I have a sign which is wrong. This one is wrong. No, sorry. Yeah, okay. Let me write exponential of plus lambda x because lambda z, sorry, because I'm on the left hand side, so I will put a c and a plus. So in this case, either lambda is chi minus c, and this one is negative, otherwise thing, and this is not admissible because unbounded. Which is actually something that I already put in this condition. When writing the mass balance, I implicitly assume that it's bounded. So it's essentially the same thing. So I'm left with only one option, which is a flat density on the left. Okay, so very easy profile so far. So it's so this one is not admissible. So I have a flat profile. Okay, now let me look at the right side, which you know, of course, very well, because I tell you it's KPP. So for positive z now, so now I change convention. I'm looking at exponential minus lambda z to have a positive lambda. So it's a c lambda equals to lambda square plus 1. Okay, so then you have several options. Okay, as you know, this tells you that c is lambda plus 1 over lambda, and this above 2. Okay, so 2 is a good candidate to be a speed, but it might not be the true one. So let's look at c equals to 2 first. Under which condition c equals to 2 is a candidate? So first candidate. Which might be in this case a minimal speed. Okay, so you can solve, of course, the equation in that case. You know that it's a double root. Lambda is a double root. So you have solution is let me write it like this. It might be rho of z, which is some constant. And I flat profile, and here I might be more precise. Let me give the constant a to this flat density. So I will have a, and then 1 plus, let's call this b, z exponential minus lambda z. Okay, with lambda the double root, which is 1 in this case. Lambda equals to 1. Okay, but now I have to find the b. Okay, A is the same. By continuity, the density must be continuous, of course. And this is given, of course, by this flux condition that I wrote there. Okay, so what is B? Is the flux continuity. B is 1 minus chi. If you compute it, if you match things, it satisfies this condition only if it's an equation for B, and B is 1 minus chi. Okay, so of course there is a clear obstruction. It's fine if, only if, E is less or equal than 1. Of course, if it's above, we will have a negative contribution after some time, and it will get larger, so it's not admissible. Okay. So this is one condition that occurs. Okay. Okay, the other side is a little bit more involved, but not that it's still a very basic computation. So second candidate is C larger than 2. Okay. But what it could be? In that case, of course, you have to compute. So in that case, there is no double root, and you expect that rho of z might be some, let's say, a1 exponential of minus lambda 1 z plus some a2 lambda 2 z. And in that case, I chose the convention that lambda 1 is less than lambda 2, and they both lie on each side of the minimum value of the parabola, which is 1. This is my convention. Okay, and again, you have to use continuity of density and flux to match the flat density at z equals to 0. And if you do these computations, so it gives you two conditions for A1 and A2, very basic tools. And this tells you that rho is A over lambda 2 minus lambda 1, a positive number. And here you will have lambda 2 minus 1 exponential of minus lambda 1 z plus 1 minus lambda 1 exponential minus lambda 2. Okay. So now there is a very simple lemma. You have to look at the one. Of course, the bad situation is when this rho of z will do something. So it will be positive because it must equal a at the origin, at 0. So it must be flat, of course, here. So the bad part is when it does something like this, when you have a negative part, and this can only occur when this one, which is largest contribution for large z, is negative, and this can occur only if lambda 2 is less than 1. So this is not admissible because non-positive if yes, because this is not a 1. Sorry, it's a chi. It must depend on my my speed. Sorry about that. And this one is again a chi. It must, of course, come from the flux condition. Okay. So it's not admissible if, as I said, lambda 2 minus chi is negative, because this one will have a negative contribution here with the wrong sign. Okay, you have to exclude this condition, and then you have to essentially discuss two things, because what does it mean? So you have your parabola lambda with 1 in the middle, lambda 1 here, lambda 2 there. Okay, so either chi is less than 1. Okay, and this will certainly be true, be wrong. You have to ensure that that this cannot occur. So either k is less than 1, and then it's this implies that chi is less than lambda 2, obviously, and so this cannot occur, and then it's admissible. This one is okay, it's positive. I have a positive density. Or if chi is above 1, then you have to ensure that the parabola has a negative value. You want no, as a positive value, because you want chi to be above, to be less than lambda 2. Sorry, you have to ensure that p, the parabola, has a negative value, which C lambda is above lambda square plus 1 with lambda now, which is exactly by a number chi. Okay, and this tells me what? This tells me that C is above chi plus 1 over chi. Okay, actually I can make it this one larger. So in this case, I am on this branch, and so if I am on this branch, it means that chi is between 1 and lambda 2, and in particular, it cannot be larger than lambda 2, so my density is again a positive. So this is not an application. This is a sorry. This is my condition. This is my condition for a positive density. Okay, so if I try to summarize that, now I will reverse a little bit, and it will be much easier to read. I have two options. Either, so my first option, let's say, is chi less than 1. So in this case, I can always guarantee that this construction makes sense. Perfectly fine. So I have a good proper candidate when C is larger than 2. But I also have a good candidate when C is equal to 2, because I have this condition here. So in this case, the minimal speed is C star equals to 2. And I have, as usual, traveling wave, even for larger speed, as described by this combination of exponential. This is very classical. Okay, and the second option is when chi is above 1. So I can rule out this case. This cannot be a good candidate. And now if I look at my second case, when chi is above 1, I have to ensure this condition. So now the minimal speed is C star is chi plus 1 over chi. So sorry, there is this chi over 2 thing with a crystal, but it's always the same formula that you can find, very similar. So let's say analogous to Fisher's equation with a cubic nonlinearity in the case where you have a weak Lie effect. There is a u1 minus u1 plus 2 chi u that was discussed in the previous talk and in Linear's. Okay, so it's very analogous, yet it's not equivalent. It comes from a different problem. And let me check the time first. Okay, in the very few minutes left, what might be puzzling, and I don't claim I have a good explanation of that, is that the threshold is not 2. You would expect 2. What does it tell you? If I put numbers, this is a 2 root RD. This is the classical Fisher-KPP equation. And this is the chi plus RD divided by chi. So it means that first case, there is no effect of the drift at all. Just the cells which are dividing at the edge, they constantly divide, and all the population is pooled. I mean, this is very intuitively clear, and it's true. It's pooled by the dividing cells, and there is absolutely no effect of the drift, which is too small. But it's too small, but not compared to 2 or to root RD. This one is the root RD. It's not compared to 2, but it's compared to half of KPP speed. For some reason, which I don't claim I have a good explanation why there is no 2 here. Intuitively, you would say that you would compare the drift with the speed, but it contributes only to half of. On the other side, when the drift is large enough, then it truly contributes to the overall speed. And as I tell you in my mass balance argument, the minimal speed is the drift speed plus some additional term due to the growth at the edge. So this is why you have this little thing that really enhance the growth speed. So a few observations that were actually a biological conclusion out of this work is that, of course, growth is important. It's essential to sustain traveling wave. If you don't have growth, if r equals to 0, that cannot be a traveling wave by just a simple mass balance equation. You cannot left cells behind if there is no growth to sustain. That was not actually clear in biophysicists' mind. Was it important and how important it is? This formula tells you that if chi is reasonably large, and E you have to think at a factor 5 between these two things in numbers, this growth term does not contribute that much in the overall speed. It's really driven, the main term, the main contribution is really this drift effect when cells try to move to catch up the oxygen front that is moving. Okay, so I think I will just again comment on because this is very basic result with only explicit computation. You can do a little bit more. You can precise. You can have a weak propagation result on the interface, but you cannot do at the moment. The PhD student Mete Demir-Sigil find a result telling you that the C star is in the middle between the limb sup and the limb sup and the limb length of the interface. So you don't know if there is a spreading for some initial data, but you know that if it occurs, it must be with the minimal speed. Okay, but it might go on each side. It might fluctuate around, and there is no clear result at the moment. And the reason is that if you want to understand the dynamic of the interface in the spreading in a spreading result, it means that you have to do the true coupling with the oxygen dynamics, because you have to track oxygen dynamics along the propagation. And this is a much harder problem because there is no comparison principle in this problem, so it's very difficult to control the thing. So you can have some weak result, but at the moment we don't have much. And there are ongoing works, collaboration actually with Chris, and some refined results around this equation. Okay, and now I will, to conclude, I will show you a few pictures. So here you see the experiment from the top. You have the initial cloud of cells, and you see after some time, I will show you the video, that some ring is forming and expanding. And then you see after 2 days, you really have a very large amount of cells in the middle, and the ring is continuing to expand. This is to tell you, and this is an introduction to tomorrow's lecture, so these are trajectories of cells. Depending on the level of oxygen, this is the oxygen gradient, the trajectories are very different. So here you see very small and random motion. Here you see very strongly persistent motion, and this will be a motivation for tomorrow's lecture. So you see in this area where oxygen is very small, below 1%, 1 or 2%, you really start to see this very strong persistent motion towards the oxygen signal. And the last thing is in the experiment, this is called a chemograph. This is time and this is space. So this is my 1D section, which is cut into time slices and reproduced there. And this is where you see that it's a very nice traveling wave moving in space at a constant speed with a constant width. And if you look at the profile, it's a constant profile. So here you see that this profile, this is a density profile. It's very different from what I depicted with an exponential followed by a flat density. There's actually a ring. In my solution, there is no ring. It's increasing and then flat. And this is because we have assumed that cells are able to follow the oxygen at any level of oxygen. And it's known that at very low level of oxygen, they cannot find their way. They are going to move randomly with a very strongly persistent motion, but without bias. So you should have a third zone without the bias, and this will give you exactly this type of profile. And one last video to show you the ring. So it's a very short video, but this is a zoom on the ring. So you have a few cell density at the edge, those cells which are left behind on the ring, which is expanding, which is made of a few width of cells. Thank you very much for the
questions. So I have 2 questions, probably very small, about so the first thing is at the very beginning, you said something like your model captures some key features, but there's ways that it's really not very faithful to what's happening in the biology. Is it this non-monotonicity, or is there more to it?
Yes. This is the first thing. This very basic computation gives you a monotonic profile, density profile, and it's clearly not. And the problem is what we try to make the next the one but least minimal grow model, and then it becomes soon and not tractable. Might be possible to make some existence of wavefront solutions, but if you want to compute things, it's very difficult. But we were sure that the speed is not very sensitive to what happens at the back. For those reasons that the main, what is really driving the ring is the ring itself, which is self-sustained and moving at the speed essentially chi, plus this additional contribution of the growth. But what is going on behind is very much not important for the dynamics. So if you have a third region without a drift, then it will have a dramatic effect on the density profile, but I guess a very small effect on the speed itself.
Okay. So maybe this is a silly question then, in light of the fact that you're saying this isn't very important, but I was curious how much of it is the change from directed trajectories to random trajectories in the back versus just a dimensional thing. So when you're showing something on a plate, the radius is increasing. So if the population is increasing, the density necessarily gets smaller, right? Because there's sort of more space. But if you put it in a channel, right, they're not spreading out in the Y direction. There's just the X direction. Does it matter at all, or does it not really matter?
So I think it does not matter in the long time. I'm pretty sure that the ring, after some days, is really nearly a planar wave.
But I guess
it does not answer your question.
My question is, like, has anyone run an experiment in a channel? Because what I'm curious is that the graph that you showed, it's sort of a huge non-monotonicity, right? You have this massive bump. But of course, I'm curious.
So that.
How much of that bump is due to dimensional reasons, like being in 2 dimensions versus being in 1 dimension?
It's a very good question.
Versus how much of it is due to the random motion. So if you did it in a channel, you might still see non-monotonicity, but maybe it's very small, and so then you can make a case to say.
Okay. I don't have a clear question. Let me answer in a very circumvoluted way. So before coming to us, this guy, essentially this guy, the first author of the paper, he did supermassive computation where each pixel is a cell, and even each pixel is a fraction of a cell in his. So it takes days of computing to make that, and it could produce the very same picture of that with individual rules of simulation. And this simulation, so this simulation actually. So I didn't mention, but this is not this previous experiment. This is called a microfluidic experiment in very controlled channel. So this is a channel, but where they control the gradient of oxygen. So this gradient of oxygen is not the one coming from the experiment. It's the one which is built by the biophysicists. So they put azote here with a very high flux, let's say air here, and they mix the two, and they create by hand this oxygen gradient. And then they observe the cells, and they observe how they move. And he parameterized his agent-based model based on these trajectories. And he could reproduce exactly the shape. So this, in some sense, tells you that, what came out of this is essentially the rule of the grow that with some overlap that I mentioned. So it tells you in some sense that I think there is no artifact due to the geometry of the fact. But of course, this is the bad news, because what is left for mathematics? If he could do everything, he could. I don't have the movie there, but could. Oh, actually, yes, I have it. If I can take 2 minutes, because I think it's actually, to me, it's interesting from the modeling point of view. So this is the simulations. So here there are many cells. There are pixels. Cells are moving randomly, and they do essentially this grow thing. And you see that it could reproduce exactly on the background you see the oxygen level. So you see that there is this oxygen which is consumed by the population, which is expanding, exactly what I said. But they were lacking understanding on that, and they were very happy to have our true contribution is to have a value for the wave speed. Because then they could really say what is important in this mechanism and what is the relative strength of each contribution. So diffusion, growth, and cell division, and bias. And then they could.
Any other questions? Okay, well then let's thank the speaker again.
Thank you.